This is the video presentation for project 22038, or cleaning of eutectic no clean solder, sponsored by Honeywell Aerospace. To begin, we'll give a short team introduction. Here from left to right, we have all of our members of the team. We have Maricruz Pavlovich, who's in electrical and computer engineering, Justin Grady, who's in mechanical engineering and is our procurement lead, Macy Ramirez Macias, who's in systems engineering and is our team lead, myself, Chucky Caquias, who's in material science and engineering, and Anisha Rodriguez, who's in biosystems engineering. To give a short introduction and background to our problem, technology has always been using circuit boards to perform electrical tasks. And as this technology has progressed, the pads and electrical components on these circuit boards has become smaller and smaller until we've reached microscopic levels. With the rise of modern manufacturing methods, printed circuit boards, or PCBs, became the norm for mass production because they're cheap and quick to produce. Modern PCBs often have circuit elements and spacings smaller than the human eye can see. And so as you can see on the rightmost photo, we have a microscopic image of a circuit board. So to give an idea of the problem that we were tasked with solving, dendritic growth is directional crystalline growth of metal named after its tree-like structure. On the right of this slide, we have a picture of some dendritic growth. The small pad spacings of circuit boards has caused dendritic growth between contacts of some of the circuits that Honeywell Aerospace has been working with, which has caused a short in the circuit and renders the entire circuit useless. This causes lack of reliability in circuits, which is a large concern when Honeywell is working with high-stakes applications. And so experimentation is necessary to understand the exact factors contributing to growth and the rate of such growth. So our objectives as a team is that we're tasked with performing an experimentation to understand factors causing this current leakage. Our independent variables in this experiment are the pad spacing, flux density, and applied voltage, and our dependent variables that we'll be observing are the magnitude of current leakage, the time before this leakage, and our ion chromatography results. Our main goal is to understand what design factors and contaminants have the greatest effect on this dendritic growth.
So how we approached the problem, our sponsors wanted the team to replicate the conditions that their PCBs go under and see if we could replicate current leakage, which would mean that we had dendritic growth. So we had to set up the experiment, and our team purchased the necessary equipment that we would need to replicate these conditions. That equipment included power sources, a DMM, a temperature and humidity controlled oven, and multiple clips and wires so we could attach everything together. The team also decided to run a 3x3 design of experiments, DOE, to find the correlation between the current leakage, which is our dependent variable, and voltage, pad spacing, and flux density, which is our independent variables. So this project has been driven by three main system requirements. Our first one being accuracy. The HPS 1009 compositional tolerances table shall be verified by the team's experimentation and ion chromatography testing. This table is proprietary to Honeywell Aerospace, so we're not able to include it in our presentation to show what exactly we're testing against. Our next major system requirement is our data. The project shall create a data set to demonstrate the effects of varying independent variables on current magnitude and time until current leakage and analysis, which is the team shall perform a statistical analysis to determine the relationship of the independent variables, voltage, pad spacing, flux density to the magnitude of the current leakage.
For the design concept of this project, it's based off the 3x3 DOE, the variables 3 being voltage, flux density, and pad spacing, and it's repeated 3 times. The PCPs have 3 different spacing. This was produced by Quality Circuits, a company that Honeywell has worked with in the past to ensure the cleanliness of the boards that was needed. How the setup works is there are 6 boards in the oven. 3 of the boards are set at a certain voltage, and the other 3 are set at a different voltage. The temperature and humidity are set at 85 Celsius and 85% humidity, and the current is checked every 12 hours. For the next few slides, it's going to be the requirement verification that we followed during this project. We have verified some, and others will be in our final report that will go with our results. As you can see, this is just a continuation of that. And this is the last one. So as a result, the first round of testing being analyzed through the ion chromatography, since there was no dendritic growth after keeping the PCBs in the oven in a week, we decided to keep it in for 3 to see if there are signs of current leakage. Our sponsors were aware of this change and were agreed with the team to keep it in longer to see if there was any change in the flux density, to see if that has any different results.
The deliverables to a sponsor was the relationship between leakage current and the spacing between copper pads, the relationship between leakage current and the amount of flux placed between the copper pads, and the relationship between leakage current and the anions found in the PCBs. Throughout this project, we overcame a problem and we also learned a lesson as a team. For this experiment, we placed the PCBs into the oven at 85 degrees Celsius, a relative humidity of 85%, and high voltages to accelerate the process of dendritic growth. However, these conditions have not been enough to enhance leakage current. The lesson learned for us would be to change our testing parameters. One parameter to change may be the testing time. We may need more than 3 weeks to get any leakage current. Another parameter to change may be the design of the circuit tested. The circuit we tested dealt with DC voltages. However, AC circuits may be of more interest. Maybe we can add AC current through the AC voltages throughout the pads, or maybe we can deal with passive components such as capacitors, inductors, components that are very common. A problem we overcame as a team was finding a PCB manufacturer. We needed to find a manufacturer that would be willing to sign a certificate of conformance stating that they would deliver to us circuits with a pollution of 0.62 micrograms of NaCl per centimeter squared or even less. However, there is no way we can continue keeping the PCBs clean once we open them. We don't have the equipment to keep them open. So maybe a lesson learned would be to change this requirement for this specific project since we don't have the equipment.
Next, we will be discussing the environment and working conditions for which the Eutectic No Clean Startup project will be taking place in, and the procedures of safety facets of the project itself. The bulk of the experimentation will be taking place at a team member's home garage, and the setup includes an environmental chamber, which maintains both temperature and humidity. There are a total of 36 wires, 2 voltage sources, and a DMM found within the whole project. And the oven itself is heated to 85 degrees Celsius. It maintains a relative humidity of about 85%. It'll maintain this range for around 1 to 3 weeks, which is a considerably long time for an experimentation in a class setting. With the setup in mind, certain safety factors were noted by the team. These include the oven constantly running, undesired shorting of equipment, water near electrical equipment, and the risk of shocks. The oven running nonstop could break the equipment and ruin multiple pieces of equipment. An initial selection of the oven and constant checking of that same equipment was the process of mitigation for the team. To avoid undesired shorts, grounding strips are employed, and the boards were set up in such a way that this wouldn't be a considerable issue. Also, checking the outlets and circuit breakers constantly occurred so that that same issue could be considered if it did occur. The next concern is the water source for the humidity near the wires. The only way to mitigate this issue was to place the voltage sources and wires away from the water itself. And also the equipment was again constantly checked for any sort of like dew growing on the wires. And the final concern is shock itself. And whenever dealing with uncertain circuits, we were sure to turn off any power sources. The next slide shows the actual setup of the experiment. As one can see, they're able to see the temperature chamber, which is on the left, the 36 wires running in, which connected the 6 circuit boards, the voltage sources, which in this case are running at 15 to 50 volts, and then the DMM used for analysis. The key issues that we have ran into include unnecessary shorts. And as talked about before, the circuit board setup, grounding pads, and utilization of baking sheets actually in the oven are meant to limit this issue. The next issue is that the constant parameters are of concern, and this refers to holding temperature, humidity, and voltage constant at their values. To mitigate this issue, we used a secondary thermometer to check temp, and voltage was constantly checked using the DMM. Time has been the biggest issue of them all. To replicate dendritic growth, it takes time for a class, especially. Time is not the most evident thing, especially when lead time for boards and equipment have been such an issue. To levy the same problem, we changed our DOA to allow for more time of the boards in the oven. And finally, one key goal was getting the boards to meet a certain cleanliness standard. The boards came clean, but we don't have a clean room, which is able to do those things. So the solution was only to really create a control board, which would serve as a set of anions, which would be found due to external concerns and then be compared to the actual experimental boards. And finally, we'd just like to thank the team, and I would like to take a second to thank both our sponsors at Honeywell and the mentors at the university. Those include Heather, Scott, Dr. Zacher, Hector, Hikmat, and Kevin, the Honeywell team. Thanks all.